Welcome to System Programming Episode 3. Today we will talk about random testing. Random testing is not fuzz testing, it's related, but these techniques are extremely useful in system programming in order to find security bugs. Fuzz testing more is in the security side, while random testing is more helpful to find all the kind of bugs that can be hiding in a complex implementation. Let's start with showing what the two techniques are about, especially random testing. So let's write a short C program. Okay, this is just boilerplate to write a small program. So I have double n, that's 1000, and I want to compute the square root of this number. And also let's print the result to the screen. Okay, it works as expected, of course. And let's imagine that I want to test the sqrt function. Basically, if I would like to use fuzz testing, I could start to write some code like I need to start a BC loop here, and at every operation I could say like fill with random bytes and give to this function the pointer of the double n, so that it could fill with random data, and then the sqrt function is called and I could wait for it to crash. So basically fuzz testing is give a random input, try to crash the program, and then if it crashes, debug the program and understand what's happening, what's the input sanitization that's not working, what's the null difference, whatever the bug is. Random testing is different. Basically, what I do in random testing is to throw input data that's random as well. For example, n can be just a random number, and I try to square this random number. Maybe let's pick a random number between 0 and 999, and then perform the square root, and then here there is the printf. Okay, because the random testing goal is not to try to crash the program, but to check if the execution is correct based on certain rules. Let's remove the printf that makes this a lot slower than it should be. For example, I'm sure that the result of this operation must be greater than 0. So I write if this condition is not satisfied, error for input n. I expect the square root of a positive number to be also a positive number. I can compile this program and try to run it, and I can keep this running a lot of time in order to cover all the inputs that I can have. Of course, it's interesting to provide random data according to a model that makes sense. For instance, a random number between 0 and 1 million will be most of the time some number in the middle, like, I don't know, this one, or sometimes this one. It's very seldom that we will have very low numbers or numbers that are at the higher range of the double. So it's important to generate the random data according to a model that makes sense in order to stress our implementation. Here what I did was I have an invariant that's the fact that the square root must be positive, and I tested for it, but this is a weak condition to test, a weak invariant, because square root could just output always 1 and it will pass this symbol condition. I can do better than that. In this case, I know that I am able to easily invert the operation, because the inverted function of square root is just multiplying the number for itself, just to square the number itself. So inverted equals s times s. Okay. At this point I can compute what's the delta between the number that I started with and the number reconstructed by inverting the square root operation. And I want the delta can be difference, can be positive or can be negative. So I take actually the absolute value of the delta. If the square root function in the C library is working as expected, this delta should be no bigger than a given epsilon number. I can compile again this program and it doesn't work. Let's check why. For sure it's an error in the Fuzz tester itself, in the random tester itself. Maybe. Okay, the problem is that if the difference is greater than this delta, I want the error, not if it's smaller. Okay, I get no errors because the implementation of the square root of the libc is working as expected. However, in this case I was lucky because I was able to invert the function. But in many real-world programs, I don't have a simple way in order to return back from the output to the input with a simple operation. So what I need sometimes is to write a different implementation of the function that I want to test in a very, very, very simple way, so that my reference implementation may be not efficient, may use a lot of space, may be lame in all the ways, but it's simple to audit, and I can say, okay, this function is almost surely same, so I can check the difference between this and this other implementation, and they must have the same output for them to be sane, otherwise one or the other is broken. So what I can do is that instead of saying inverted, I say S2 is sqrt symbol the n. So I write this symbol implementation of the square root, and then I test that the difference between S and S2 output must be small. And if instead it's great, I have some problem. Let's write this simple implementation of square root, double sqrt symbol the wn. Okay, we need to figure out a very simple algorithm that is able to compute the square root, and we must be pretty sure that the algorithm is so simple that we can audit it, can review it, and the output should be same. So, for example, well, a very simple observation is that like I have an increment of 1, and I can say like while forever do like my target, my result is initialized to 0. So I can say while my result squared is less than my target, then I want my result, but sorry, it's if the current result that I have is multiplied by itself, is still smaller than the number that I want to perform the square root of, then I increment the result by this increment number. And if we go outside of the while loop, it means that at this point we have a result that is multiplied by, that is greater by the actual square root of the number n. So I do a step back and do the same operation again, but this time I use an increment step that's 10 times smaller, and we can say that we continue until the increment is greater than a very small number. So when I reach an increment that's so small, I say, okay, I'm okay with the result that I obtained, and at this point I return the result. So why this should work if I don't have bugs? Because, for example, let's imagine that n is 25. Okay, I start with 1, and I say I start with 0, and I say 0 for 0 is less than 25. Yes. So I do the same with 1. 1 I increment, currently increment is 1. So 1 times 1 is less than 25, yes. 2, yes. At some point I arrive at 5, and I say, is 5 times 5 times 5 less than 25? No. So I return to 4, and I start to increment smaller numbers, and so forth, so forth. Of course, we should have something like that here. If the result is exactly equal to n, I should just return it because I found my answer. Okay, so this is an optimization in order to output the number when it's an integer square. Okay, let's see if this works or not. So looks like it's outputting the correct stuff. Let's compare it with the actual libc implementation. Okay, the two numbers are kinda similar. At this point, I can finally try my random test. So I have the two results from the two independent implementations. I didn't use any clue about how the real sqrt is implemented when I implemented my simple version. So they should file for different cases if they are both broken. Okay, let's execute it, and I get no error, so I can say yes, probably it's working as expected, and the two implementations are both correct, so I have no bugs. But this was a very simple case. Let's see how this technique is used inside Redis in order to improve the reliability of the server. For instance, inside tests, unit tests, that's a good one. The geo-indexing feature of Redis allows you to set coordinates in the Earth surface, and then you can perform range queries for radius. Like you say, in this point of Earth, I want to understand all the points that I add that are within within 10 kilometers from this point. And this is a complex implementation inside because it requires some math and also doing low-level bit operations inside sorted sets scores, because it's a two-dimensional indexes and it uses interleaving the bit representation of the longitude and the latitude. So it's a bit of a complex code, and it's very easy to make bugs there, to create bugs. So what I do is to write exactly an implementation of GeoRange in Tcl, and I then see if the two implementations return the same set of points. So what I do is basically to start, I generate a radius I want to query. It's interesting that what we said early is that we need a randomized model that makes sense and is able to stress, for example, the extreme of the range. So I want random int 10 means just extract a number between 0 and 9. And if this number extracted is 0, so 10% of times, I use a very big radius. And it's useful to stress the implementation, some part of the implementation. However, normally I want to use the radius that normally the users will use, like from 0 to 200 kilometers. Then I have a radius, and at this point I generate a number of random points. Here I generate actually just one random point. Okay, this is the random point is the sender of the search point, and then I have to and then I generate 20,000 other random points that are the points in all the Earth surface, and at this point I can see, okay, I also add the same points in a Tcl list, and I add the same points in Redis. This R is the Redis client object, so I use geo add my points, and this expands the vector in the list into multiple arguments. And at this point, I want the result from Redis, and I also computed the result in the Tcl side, but the way I computed the points inside the search area in Tcl is the most basic way. For every point that I add, I compute the distance between the search point and this point longitude and latitude. At this point, if the distance is less than the radius, then the place is within the radius, otherwise it's out. So basically it's very hard to make errors in a so simple implementation. The implementation is simple because it's terribly inefficient. If I have 1 million points, I have to scan them all to see if each point is inside or outside, while the internal Redis implementation is much smarter than that, of course. At this point, if the two results don't match, I throw errors and I debug. I provide debugging information so that I can reconstruct the state of the failure and investigate it. This was an example. There is another one that's, in my opinion, pretty interesting. That's the Redis Radix tree implementation. Radix tree is a very cool data structure, but is very complex to implement. Let's see, it's full of mem moves and also node splitting. Let's see if we can find. Okay, this is, for example, the function in order to insert a new element, and there are multiple algorithms possible depending on the node we stop into in order to insert. So sometimes we have to split, create an intermediate node with two children. Other times we want to continue the algorithm to append to the rest, and it's complex. So there is like algorithm number one, algorithm number two, depending on the case. This is the comment. The code is smaller than the comment, but it's complex. So I want to be pretty sure that the implementation is sane, because this thing is used inside the Redis cluster. It's used in order to implement the new streams data structure and so forth. This Radix tree also has like the ability to perform iterations. Like I have like a cursor and I can go back and forth. Let's see if I can show you. Okay, random walk test. Basically, I can add items. This is just an array of C strings, and I insert them all. And I can like create an iterator, start it, seek it. This is just regular expressions. It means seek the first element. But I could say like seek greater or equal to that string or whatever. So it can seek with normal operators like less than or equal, greater or equal, or first element or last element, and so forth. And I want to be sure basically that the Radix tree implementation of the scanning of the items is correct. I can seek the right element, and I can then see all the elements when I call Rax next function. I want to go exactly to the next one, the string that is immediately greater than the current one, and so forth for every call. This is one thing, and then I also want to check that the Radix tree dictionary itself works as expected. I can add all the keys, I can retrieve all the keys with the associated pointer, and the pointer value is correct, and so forth. So how do I do that? Basically, what I do is to create a very simple implementation of the hash table. The simplest dictionary that I can write is an hash table with fixed table size using always chaining in order to resolve collisions. You see struct ht node here next. So there is no way to like reshard this hash table. It's fixed with a fixed number of buckets. And I must have very similar operations to the Radix tree. I have the way to create a new hash table. I want the one function to perform the hashing of the element. I want the ability to look up a new element. Let's see, the code is like 10 lines of code, even less. And adding a new node is equally simple. Removing a new node is extremely simple, and finding the node, everything is very simple. Okay, so this is the whole implementation of the hash table. It's like a job. It's something that I can make sure that is bug-free. After reading it a number of times, I can be pretty sure that it's very hard for this implementation to have the same bugs that the Radix tree could have. The key point here is that I'm okay even if it being bugged, but having different bugs compared to my Radix tree, because any difference in the implementation will be spotted, and I will fix this one till I can really check the other and so forth. Okay, that makes sense. Then I have function in order to generate random keys, and I want to generate those keys according to different data models. So like alpha key, or I want sometimes completely random keys, or I want to use a very small character set so that the Radix tree is able to compress the nodes very well, and so forth. Now, let's see how the Fuzz test, note that it's wrong here, the name of the function. It's not Fuzz testing, technically it's random testing, but we know the difference at this point. We perform random operations on both the dictionaries. So we insert the elements here, we insert in the hash table, and we insert the same data in the Radix tree. Then we also remove elements with a given probability, and then we start to perform the checks. First of all, we want to be sure that the count of the keys is the same. Then we use the Radix tree iteration in order to enumerate all the elements, and we check that the value of the two elements is the same, and we also increment the number of keys in order to be sure that Rax next really returned every key inside. And at this point there is the verification data, and that's all. However, in this way I was just able to test that the dictionary is okay, but what about the seek and the walking functions? I have a different random test for that, and it's based on the same sorted data structure implementation in the terms of that hash table. So I populate the hash table, and then I basically call qsort against it in order to create basically a linear array of elements sorted. Once I have an array of elements sorted, it's very simple to replicate the same operators I have to seek inside the Radix tree in terms of linear array. So basically this is the implementation. As always, is extremely simple. And finally I can implement the Fuzz test for the iterator. So basically I add keys according to a given key model, alpha, random, whatever we saw, and then I perform a random seek operation. I choose random seek operator. I also seek to a random element, And finally, I start to compare that all the elements returned are the same, basically. And they must be the same. And also they must agree about the end of files, so they should report the same number of elements. Here there is the mem compare that compares the two returned elements, and if there is a problem, I want to enough output in order to fix this problem. Let's see how this works in practice. Here is the test against the hash table and the Radix tree, and then I start with the other test about the seek and next and prev. It takes some time because if you want to explore enough states in your code, you have to use like a lot of keys. Here we are using like 3 million, but the next tests are even bigger than that, and okay, it takes a lot of time, but basically, well, that's it. I believe that because of the massive use of random testing in Redis since the start, almost all the kind of data are tested like that. Lists or sorted sets, score ordering, even the replication is tested like that. We generate a random sequence of commands and then test that the slave has exactly the same data set as the master. So basically the same technique is used everywhere inside the Redis implementation. Okay, this is the iterative Fuzz testing, random testing actually, and it performs like a lot of, it's very fast implementation, so you can imagine every second how many things are tested, and it's very hard for the implementation to be bugged and still be able to pass this test. One last thing that's very important, when I find a new bug, for example writing a given edge case unit test and I find a new bug in my implementation, what I do is to try to modify the Fuzz tester so that it is able to spot this bug, just improving the way the random data, the random input is generated. In this way, sometimes after I find a bug using just, for example, a code review, I can spot several related bugs because I improved the model in which I generate the random number. Okay, that's all, and I hope you liked this. Bye, have a nice day.